Good morning, good afternoon, or good evening, everyone. It's a pleasure for us to talk to you from the Cryosphere Pavilion from COP30 in Belém. And this morning we have the pleasure to talk about the tipping points, specifically Antarctic tipping points, which is part of a big project that we are having together at international level with the World Research Climate Program. So today's our speaker are Anastasia Romanou from Columbia University and Jonathan Whaley from Grenoble Alpes University. And so I think I will let the floor to them. We'll start with Natasha that will present the program and the initiative that we are having in those months with many scientists over the world about assessing tipping points in different climate elements of the planet. Thanks. Okay.
Hi, I'm Anastasia Romanou. Can you see my slides? Jonathan, you can give me a thumbs up if you can see my slides. Okay, good. So, so I'm here. Thank you very much for the invitation. I'm very happy to be here with you virtually. I would have preferred to be at Belém with you. It's a very exciting time, I hear. So I will be talking about the assessment report that the scientific community is putting together under the auspices of the World Climate Research Program and the Safe Landing Climates. And the effort is being led by Gabi Hegel from University of Edinburgh. I am from Columbia University in New York, and I represent the writing team of the Tipping Points report. First of all, why has been such an why this report is coming about is the incredible interest that has been shown in the scientific community about the topic. There has been an explosion of literature the last 10 years. It started in 2008, but really doubled over the last 10 years, and the citations tripled. So this is, for example, a diagram that you can see from Web Analytics from Web of Science. Now, the question is it really a North issue, a global North issue? You can see that most of the publications that I was talking about, they come from countries like the US, the UK, Germany, the entire Europe, Australia and China. Is it really an issue of the developed world? It shouldn't be, because we know that tipping points have important implications for the ecosystems around the world, and therefore there should be much more interest, scientific interest and production from other parts of the world. But of course there are a lot of issues regarding this, and it should be noted. The majority of the publications, more than 3 times as much, is coming from Europe, and that is also another interesting point that we want to investigate why it is happening. This same trend that we are seeing in the general literature, we also see in the assessment reports. Tipping points have featured in AR5 that you can see here, the Intergovernmental Panel for Climate Change Assessment Report 5, in 40 of the pages of that report. Whereas in the most recent report, the AR6, in 2021 to 2023, it appears 63 times in the Working Group 1 Physical Science Basis report, 135 times in the Impacts, Adaptation and Vulnerability report, and 41 times in the Mitigation and Climate Change. It's clearly driven, the interest is driven and peaking at in Working Group 2 at the Adaptations and Vulnerability research, because it is a topic that affects greatly the societies. Of course, there are more specialized reports, like the Global Tipping Report, which is coming out of the University of Exeter, and has a more broader and in-depth assessment of tipping points. Plethora of literature in the last 10 years. As you can see here, we have tipping elements, mechanisms and impacts, opportunities for Earth observations. How do we observe tipping points, how we should observe tipping points, what observations we need, mechanisms, cascades, and early warning signals. A seminal review of the topic came in a few years ago in 2022 and placed for the first time the tipping points in the context of global warming levels, meaning that when we exceed a certain temperature threshold, we have a much higher probability of triggering that tipping point. And what are the tipping points? The tipping points are the Atlantic meridional overturning circulation that you can see in this map, the ice sheets in Greenland and in Antarctica, boreal permafrosts, Amazon rainforest, of course, and then more regional tipping points like the boreal forests, the mountain glaciers, the monsoons, and the coral reefs. Of course, the global tipping points, they are called global because if they tip, they have consequences across the world. Whereas the regional tipping points, they might affect regional ecosystems, and they have therefore less extent, geographical extent, but the importance of the impact is still large. Now, the report showed that the most imminent tipping points, those that are triggered below 2 degrees global warming threshold, are the Greenland ice sheets, the subpolar gyre in the North Atlantic, and the boreal permafrost. Whereas, for example, the West Antarctic ice and the West Antarctic ice sheet as well. Later, between 2 and 4 degrees global warming levels, we expect to see increased likelihood of tipping in elements like the Amazon rainforest, the Sahel, and the West African monsoons. And of course, at the high warming levels above 4 degrees C, we expect to see destabilization of the boreal forest, the Atlantic meridional circulation, and permafrost. And in a more recent study, we linked extreme events with tipping points, and that is another viewpoint of understanding how the climate system works and how interconnected everything is. We know from the assessment report, the 6th assessment report of IPCC, that extreme events are increasing in frequency, in duration, and in intensity. And and especially compound events, extreme events, are likely to trigger the stability of the Earth system. For example, in the Amazon, compound extremes of drought, wildfires, and heat waves can bring about the dieback of the Amazon earlier than what the previous warming levels showed. And the same happens for the Atlantic meridional circulation, which is sensitive to changes in sea ice distribution and melting, and of course heat waves, and the boreal forest wildfires and extreme heat waves, and so on. Other recent studies focused on the cascades between the tipping points, the domino effect. One of them tips, and then that causes the other one to tip. For example, the Amazon, the AMOC can change the internal variability, the El Niños and the La Niñas, and that can have huge effects in the Amazon rainforest and can cause it to tip, and so forth. There are connections, as you can see, all these red and blue arrows are showing that all the tipping points are interconnected and they can cause a domino effect. Additionally, recent studies have focused on the mathematical tools that we have, like early warning signals, mathematical tools coming from dynamical systems theory, from statistics and so forth, and Bayesian analysis. And we are looking at how these extreme events can be predicted, if they can be, if we can use early warning signals in the climate system that can tell us that we are approaching or how far away we are from a tipping point. And this is a very important research that is just starting also to develop, and we are looking forward to the results that are coming in the next few years. Modeling activities have peaked as well. Breakthrough activities like the TIP-MIP, the Tipping Model Intercomparison Project, has already garnered a lot of interest from research groups around the world, in North America, in Europe, in South America, and in Australia and Asia. And that seeks to answer some of the key questions we have with regards to tipping points, how far we are from crossing, what are the key feedback processes, the characteristics, uncertainties, interactions, and reversibility. This project has launched a couple of years ago. It's in the progress of getting information, getting all the data from the modeling groups and analyzing it. By the time that we will have the report out, we will be able to produce some of these results. And that's the space that these high impact events and tipping points report that's sponsored by WCRP is coming to fill out. That's a space. We need a consensus building across the scientific community, particularly ahead of the next assessment report by the IPCC. We need to holistically treat tipping points and high impact events from drivers all the way to adaptation, bring together physical science and socio-ecological impacts, and of course address some of the communication issues that surround tipping points. Communication issues that not only within the community, of course, the scientific community, we get to agree what is a tipping point, how fast it will tip, what are the impacts, but also the communication to the public, communication to stakeholders and policymakers, which is very important in order to the community, the society, to be able to prepare to address important topics, important effects like this. The report structure focuses on definitions. We have spent a lot of time trying to refine the definitions and unify them and combine them. And then, of course, the description of the tipping elements in different Earth system components, like the ocean, the cryosphere, the land systems, the tropical land systems and the boreal land systems, how impacts, how the tipping points will translate to impacts in the socio-ecological world, outstanding uncertainties that exist in terms of modeling and understanding, and the gaps we have in observations, and lastly, some recommendations for research in the upcoming, in the scientific world, but also the assessment, the IPCC assessment. The author team is huge. There are 70 people from 16 countries. That's how many I counted, but there might be more. And the emerging issues, the early results, what they are showing us is that how to better treat and understand deep uncertainty which is associated with elements that have high impacts but very low probability, almost unknown probability of happening, Earth system modeling gaps and biases, observational needs that we have, not only modern observations, but also how do we bring in and utilize paleoclimate evidence and how applicable that paleoclimate evidence is, impacts in ecological and human systems, and of course misinformation and misinterpretation of scientific results about tipping points. The research questions, I've talked about them. What are the processes that lead to the tipping points? How large the scales are? What are the thresholds in terms of forcing and in terms of climate state? How lasting will be the transitions to tipping points? How to better enable early warning and signals and predicting the risk of tipping points? How do we analyze the plethora of data, the huge amounts of data that are coming into us from different modeling intercomparison studies and observations, and extract this very low frequency signal that's the tipping points. And how do we, of course, communicate tipping points to policymakers? Some recent results from this report, as I said, that we have defined better the traits of tipping points, traits such as abruptness, irreversibility, feedbacks, cascading effects, threshold bridging, you can see here different ones, and a lot of other notions associated with tipping points. And we are also looking at different forcing levels and spatial and temporal scales. We are looking at tipping points that have to do with bifurcation in the climate system. That means that changes in the system that can take a very long time to develop, but also noise tipping, which is actually triggered by extreme events, and it can happen anytime, much earlier than what we think from just the bifurcation theory. And of course, rate tipping, rate depending tipping that comes about because we keep emitting greenhouse gases at accelerated, ever faster rates. And so that is very important to look at these different dependencies and understand how tipping points may be happening and how that affects the probability of them happening in the near future. And lastly, in the report, we have some early results that I can show have to do with climate and socio-ecological system interactions. Tipping points will affect climate impact drivers, the extreme conditions in places, hot and cold, heat waves, cold spells, precipitation, extreme river floods, any other kind of flooding, landslides, storms, windstorms, snow and ice extremes, like the thawing, the time of the thawing of the snow and the ice, erosion at coastal areas, etc. And all these impacts that physical impacts that tipping points will have will of course translate down, cascade down to human systems, and will increase our exposure, vulnerability, and adaptive capacity to the tipping points. And of course, these effects will affect our food systems, our built environment, displacement and human migration, health and economy, and many other aspects of our societies. The WCRP report is coming into a very opportune time, because just ahead of the assessment report 7, and we will be able to inform Working Group 1, Chapter 8. It's the first time that IPCC will devote an entirely new chapter to abrupt changes, high impact and low events, and critical thresholds, including tipping points. And that report will depend heavily on the WCRP report that I've been talking about, and will link to other working groups which look at the impacts, the adaptation and the mitigation of climate change. And hopefully this time AR7 will have a much broader and much more nuanced coverage of those low likelihood events, which though can trigger climate state changes. And this is, thank you very much for your time. The report will be coming out in 2026. We had 2 great meetings, one in New York and one is coming up actually in Paris, which will finalize this report and bring the community together to be able to present it to you. Thank you very much for your time.
Thank you, Natasha, for the great introduction to the matter. So I suggest we move on, and if there are some questions, we can take them at the end of the session, actually. Yeah, so, okay, perfect. So I will be together with Jonathan focusing on the Antarctic tipping point, as we are in the Cryosphere Pavilion and we are both glaciologists, actually. So we wanted to illustrate how what Natasha actually explained in this specific case of Antarctica. So, well, first of all, what are the tipping points in the cryosphere system? A cryosphere system crosses a tipping point when changes are abrupt. Okay, small additional change just trigger a very large response of the ice sheets. When they're self-amplifying, so it means that a little warming causes some melting, the ice sheet decreases in elevation, it's even warmer, it causes further melts, so it's a positive feedback, okay? So that's a self-amplifying tipping point. And when it is irreversible on our timescales, because on geological timescales there is nothing irreversible, so you have to understand the irreversibility here is linked to the timescale at human multi-generational, let's say, horizons. So irreversible in the sense that if we lose the ice, it's not going back that easily in a very short amount of time. And in this case, they are linked to very large deep uncertainty, okay? Because we lack of knowledge of some of the physical processes that we don't know, and so we need some additional observations to validate the physics that we put in the models that allow us to project and understand those potential tipping threshold actually linked with the cryosphere. So Antarctica, if it were to melt totally, would increase sea level by 58 meters, okay? Among which 4 meters are accumulated over West Antarctica and 52 meters over East Antarctica. What is really important in terms of to understand for Antarctica is that if we remove the ice from the Antarctic continent, you can see that on the blue area, I mean, the ice sheet is grounded below sea level, while on the reddish areas on this map, you can see that the ice sheet is grounded above sea level, and this is very important for Antarctica because it means that in the blue sectors where the ice is grounded below sea level, it is not only vulnerable to atmospheric warming but also to oceanic warming that just comes to the ice sheet margin. Well, the ice is flowing toward the ocean, and when the ice reaches the ocean, it starts to float, actually, okay? And because of the ice density, it starts to float, and it expands above the ocean surface. It's very thick, actually. At the front, it's like about 300 meters, and at the grounding line, the last point that just touches the ground is about 1.5 kilometers, okay? So it creates a huge cavity in which the ocean is able to flow, okay, and bring the heat directly to the ice sheet margin. You can see on this map, this is a map of satellite observation of the ice velocity at the surface. And those ice shelves, when they flow over the ocean, they accelerate because the ice flow doesn't encounter any friction at the base, not like the ice that is flowing on land that is experiencing friction when it just flows on the ground, okay? So when the ice shelf flows on the ocean, it's just accelerating and create this very huge ice flow acceleration in general. Sorry. Why ice shelves are so important? Because they are the typical tipping elements of the Antarctic ice sheets. Actually, the ice shelves, when they flow on the ocean, they flow as taps somehow, and they slow down a little bit the ice discharge coming from the inland Antarctica. And so if we were to remove them, the ice flow would accelerate and the discharge of the mass loss would be even greater and sea level would rise even more quickly and further. So what is important here to understand is that there is a counterforce to the inland ice flow that is called buttressing. This buttressing slows down the ice discharge, okay? And if we were to remove some ice in the ice shelf, this buttressing effect, so the counterforce to the ice flow coming into the ocean, would definitely weaken, and so it will allow even more ice discharge to come, and will cause a very rapid sea level rise. Okay, so the buttressing force is really key in this case because this ice shelf, they really maintain this buttressing high. And if the ice shelf weakens to some extent, this buttressing decreases, and this favors the ice flow discharge into the ocean. Well, the ice shelf, they satisfy all the criterion of tipping points, actually. They are abrupt. I mean, if they thin, if they calve, if they collapse, okay, it's a very abrupt process. It causes a self-amplification, so when it starts collapsing, it just continues until the the glaciers stabilize again in a very stable position of the bedrock, okay? They're irreversible. Once you lose the ice shelf, it takes over decades or centuries, even sometimes for the bigger ice shelf of Antarctica, millennia to really grow up again. And as I say, there is some deep uncertainties because today we are not able to get a lot of observation in a continuous way with a large spatial coverage of all the ice shelf around Antarctica and also below the cavities. And that's the main problem for us because we rely on a physics that we are not able to validate totally. And that's a problem. And this is one of the main sources of the uncertainty in sea level projections. So this kind of tipping actually is called bifurcation-induced tipping, means that we start from a initial state with the ice shelf that is expanding on the ocean and goes toward collapse of the ice shelf. So ice shelf is there, ice shelf is not there, it's a bifurcation. But it's also a rate-induced tipping because it's caused by the ocean warming, and I will just explain that in a minute. So how fast is it when an ice shelf collapses? It's about 2 centuries, but the trigger is fast, meaning that we pass the threshold in a very little amount of time, so a few decades or a decade. I mean, if some of the ice shelves are very close to their thresholds in terms of warming, could be even tomorrow. So the trigger is fast. But there are some long-term consequences because the ice shelf is collapsing, and it takes a while for the ice shelf to collapse. If the ice shelf is very small, it can collapse in a few days. If the ice shelf is big, it can take a few decades to really collapse. But the collapse is not stopping at the ocean part. It also propagates inland, and I will also explain why. Basically, this is an example of simulation of ice shelf collapsing in this part of Antarctica where you see the blue square here. You can see in the simulation starting in 2015 and ending in 2300, so 2 centuries ahead in the future. You can see how fast this part is disintegrating. So you will tell me, yeah, 2 centuries is not fast, but actually it is fast because it means that it starts today, and little by little we will see an acceleration in this retreat of those ice shelves. Well, the first driver of this collapse, of course, is the ocean warming. As I told you, that the ice shelf, when they float, they form a cavity that allows the ocean to flow inside and bring all the heat to the Antarctic margins, actually. And so this figure shows you broadly the temperature around Antarctica of the ocean. And you can see that in some areas, very close to Antarctica, the temperature are more red. So it means that the water is warmer, but warmer, it means like 1 degree. It's not, we are not in the tropics anyway, but 1 degree is warm for an ice sheet that is minus 20 degrees at the margin, okay? And then you can see in other sectors very close to Antarctica, it's blue, so it means that the water there is not as warm as in other sectors. But you can also see, I mean, so why is it important? Because in the area where the ocean water is already warm, the ice shelf are already getting a lot of heat from the ocean. In the other sectors, we think that as the ocean is warming, in the future, the state might change, and we will have what we call a regime shift in the ocean conditions. So we will have like cavities that have colder water flowing inside, transitioning toward a cavity where the heat will be brought to the margin on more regular basis, okay? So this is what we call the regime shift of the ocean cavities. And this is really important because for now we have only, let's say, a big one sector in West Antarctica that is affected by a direct advection of heat from the ocean. But in the future, this might affect the entire margin. This is what the satellite tells us about the state of the ice shelf over Antarctica. I mean, all this big cycle shows you how intense is the mass loss from the ice shelf due to the ocean warming, and so the thinning of the ice shelf at the surface. I mean, these studies report that out of the 162 biggest Antarctic ice shelves, because there are more than 300 ice shelves around Antarctica, but the biggest, 71 have a visible mass loss since the 90s, actually. And so that's a very obvious sign that Antarctica is really vulnerable to what's going on in terms of climate change. The second driver is about what we call the ice shelf damage. So when the ice is cracking and when it forms iceberg at the front that then drift away with the ocean currents. So what happens when what we call the damage? Okay, so you have the ice shelf flowing on the ocean surface, and then at some point there's some obstacles, topographic obstacles on the ice flow pathway, okay? And this creates some internal deformation of the ice because the ice is a solid, but it's also flowing very, very slowly. But so it creates some deformation, okay? Because of the deformation, you have some small cracks that start forming at the front of the ice shelf. And this happens while the ice shelf is advancing. When the damage is too high, when the deformation is too high and forming too much cracks, then the ice shelf is calving, so the front is collapsing, creating some iceberg, and this makes the ice shelf to retreat. Of course, it's losing some ice, okay? So that's a natural cycle of the ice shelf. Normally, if the ocean is not too warm, the ice shelf advances again, and then back again when the front is cracking, creating new iceberg, advancing again, etc. But now in a warmer world, what about having some feedbacks about the retreating ice shelf? So if we stay in this state of retreating ice shelf, because now the warming is too fast for the ice flow to really compensate for it, then we have this loop. We create some ice acceleration because we remove a little bit of ice at the front that, you know, as I say, with the buttressing, act as a stop or slow down of the ice flow. Then it creates even higher deformation of the ice on the ice shelf, which create more damages at the front and then create even more calving, but on a faster time scale, okay? And in a way that this feedback is always accelerating, and that's how we create an ice shelf to collapse, okay? So that's the second driver of our ice shelf tipping points, the damage and the ice deformation that is not able to be compensated for new cooling or new snowfall at the ice surface. Then we have driver 3, which is about hydrofracturing. So it means that we have an ice shelf, okay, that we will receive in the future more ocean heat. It will thin because of the ocean melting from below. But at the surface, the ice shelf will start to also melt because the atmospheric warming will still go on, okay? It will create some meltdown and new fracture. And then, because of this new fracture, the front will be calved in a very dramatic way, okay? Because during winter, the water will freeze again and will create new cracks in the ice shelf, which will allow, more damage, as we just saw before. And this process is called hydrofracturing. Actually, we all experience that, and we are all very careful in the winter not letting the water tube open just to avoid this kind of problem, right? So it's exactly the same processes here. I mean, you allow the surface meltwater to infiltrate, make new crevassing, and accelerating this ice shelf demise. Okay, so what are the response of the ice shelf? Because we are cracking the ice shelf, because we are thinning the ice shelf, we are weakening the process of ice shelf stability and the fact that they are slowing down the ice discharge from inland ice, actually. And this creates some instability. So we have ice shelf thinning due to ocean warming, and when it's too thin, when the ice sheet is not able to sustain the platform, the floating ice shelf anymore, then it cracks, it collapses, and it makes the glacier to retreat back, which is what we observed in some of the case of the ice shelf that also already cracked in the peninsula of Antarctica, for example. And that's retreating back of the glaciers means that we lose a lot of volume to the ocean, okay? And this one is called marine ice sheet instability. Then we have another one that is also due, in addition to this thinning of the ocean, to hydrofracturing at the surface, which amplify further the instability and allow the ice sheet to retreat even more, which means even larger ice discharge and mass loss to the ocean. So, as a conclusion, we have seen this loop of tipping point and feedbacks. So we have an ice shelf that is thinning or damaged, and because of our ocean warming, because of our atmospheric warming, and because of the one that is projected into the future also, that leads to a kind of bifurcation state where the ice shelf is unstable and will collapse. Okay, so we will pass very quickly from a state where the ice shelf is there, and then the ice shelf is gone. Okay, and this creates an acceleration of the ice discharge into the ocean, and then thus an acceleration in the sea level rise. Okay, because it will contribute to even more mass in a very short amount of time. Of course, what we project based on the last IPCC report, but also on the more recent paper, is that right now, if we account for this kind of loop, we are up to 1.5 meters by 2100. And over 2 centuries, as I explained, because it's a process that still goes on for a few centuries, we project up to 10 meters, because as I explained, it's a runaway process. It's a self-sustained collapse, okay? And then we have a lot of deep uncertainty, okay? But as I say, I mean, the processes right now, the projections of trying to model these tipping points are very model dependent, because we have very few observations, so we lack of observations. Because of that, the model disagrees on the tipping point, because not all the models incorporate the same kind of physics to really reproduce this kind of tipping points linked with the ice shelf stability. And so the risk is that we have faster than projected sea level rise, which is exactly what's going on. If we compare, some recent studies just already make some feedback about where we are now in terms of sea level rise, the trajectories, and what happened 10 years ago with the IPCC report. And we are already, we were too slow, actually. We are too fast. Now the process is too fast. It's faster than what we projected. So the early warning for us is like to still monitor all those ice shelves to understand if they are still thinning over time, okay? If there is some ice flow acceleration, because that's one of the, let's say, signal that the ice shelf is really losing some mass. If the grounding line retreats in some marine-based sectors where I say the ice is grounding below sea level, so very vulnerable to ocean warming. And yeah, if we can definitely expand the network of remote sensing from space to have a large coverage of Antarctica, but not only, going to have observation within the cavities that we think are the most vulnerable, to be able to understand before they collapse how is the state and what could be the tipping point, and also monitor the one that we think are already collapsing somehow. Okay, so I've finished here. Okay, sorry, Jonathan, take me a couple more minutes. So yeah, now we'll pass over with Jonathan that will explain you most even faster meteorological events that can cause also the ice shelf collapse. Over to you, Jonathan.
Okay, so, sorry, let me just get the thing to go. All right, can I just get a confirmation that you can hear and see my slides? Perfect. Great. Yeah, thank you, Flo, for providing the framework and providing the introduction to tipping points in the cryosphere and how they relate to Antarctic ice sheet collapse. My talk will be more focused on the weather aspect and how extreme weather can actually impact ice sheet stability. Let's see. There we go. All right. So when you often hear about extreme weather, you often hear about in the context of a black swan event. What that means is a black swan event is an extreme event that is highly consequential, but it was not thought to have been possible before. But when looking back, maybe it should have been possible. Now, in the context of climate change, black swan events are becoming more possible because we are entering a new climate state where extreme events are pushing the envelope beyond just the small margins we would expect before. What I'm talking about is, in a stable climate, if you had extreme weather, perhaps the temperature record would be broken by 0.1, 0.5 degrees. But in our new system that has been now heated by greenhouse gases, extreme weather can actually break previous records by really large margins. One example of this is the 2021 Pacific Northwest heat wave, where regions of British Columbia broke their all-time temperature record by some 5 to 6 degrees Celsius, and then resulted in a town of Lytton burning to the ground because of this heat. Another more recent example of this was Hurricane Melissa, which made landfall in Jamaica just last month. This was a incredibly powerful Category 5 storm where rapid attribution climate studies showed that the maximum winds of the storm were some 10 to 15 miles per hour higher than what we would have expected because of the warmer ocean temperatures. Now, I put all these dice in the background because basically having these extreme weather events is the equivalent of rolling a pair of sixes. But with climate change, we are essentially loading the dice and making it more possible to throw a high number and, well, unfortunately, in reality, have something that is highly consequential for human society. Now, not to be left out, in Antarctica, oh, that's strange. The slides are not appearing, actually. That's strange. Are you on the screen there? Do you see a full all the images, or do you just see one image?
Not appearing here on the screen too. I mean, just half as for you.
Okay, interesting. Let's see. All right, let me try something real fast here. Yeah, it just says image can't be displayed. That's new. Let me try something real fast. Sorry for the technical issue. Let me try restarting my PowerPoint because it was just working before. Hold on. I'm very sorry about this. Okay, now let's try this one more time. Slideshow, concurrent slide. Am I sharing my screen too still? No, I gotta do that again. Okay, from current slide. Okay, is that better? Can you, okay, I think that should be better now. All right, perfect.
Yes, it is.
All right, sorry about that. All right, where was I? Oh yeah, Antarctica. Yes, so we've also had a black swan event happen in Antarctica back in 2022, when we had a record-shattering heat wave that occurred over a large portion of East Antarctica that actually caused the largest temperature anomaly ever to be recorded on the planet. This was some 43 degrees above normal at one weather station deep in the Antarctic continent. And in this image, we can see just how expansive this heat wave was. All the areas gridded here actually exceeded their March temperature record from the past 40 years or 50 years. And just to remind you, this area is about the same size of Australia. This truly was a massive heat wave. Now, for the people who were working in Antarctica, this relative warmth was a fun day to go outside and enjoy the beach weather. However, this event also had real consequences for the ecosystem. One was this storm, basically, this heat wave triggered the final collapse of a relatively small ice shelf in East Antarctica. In this image, we can see that in the beginning of March, before the storm happened, we had this ice extending from the Antarctic continent out to this little island over here. But then after the heat wave ends, now this ice has been completely disintegrated and the ice shelf, the Congar ice shelf, has formally collapsed. When we look at the satellite imagery during this heat wave, we see actually what we call an atmospheric river transporting huge amounts of moisture from the lower latitudes and from the subtropics onto the Antarctic continent. You can see the cloud pattern here, this very large storm, and then the warmer colors, the greens over here, we see these really high water vapor values being evected, being transported onto the Antarctic continent. So I mentioned atmospheric river. I should probably define what that means a bit. So basically, an atmospheric river is a mechanism for transporting moisture from the tropics and subtropics down to the polar regions. Looking at this image here, when you see these little thin bands extending from the tropics going up to California over here or going towards Antarctica over here. Those are the atmospheric rivers, and they are a very important part of the global hydrological cycle. Now, they are relatively rare events in Antarctica, but they actually do represent the majority of extreme weather that we experience on the Antarctic ice sheet. There's been a lot of research recently in the past couple of decades about how these events have triggered massive heat waves, heavy snowfall events, sea ice disintegration, and in this case, ice shelf disintegration. This schematic here is showing you the processes of which an atmospheric river actually weakens an ice shelf and can then potentially trigger the collapse of that ice shelf. In this example here, we have the atmospheric river making landfall on the windward side of this mountain range. When the warm air and moisture then goes over the mountain range, it descends and warms in the form of this firn event. This very warm firn then causes surface melting and melt pond formation on the surface of the ice shelf. And as Florence explained before, that leads to hydrofracturing, which then can destabilize the ice shelf and cause calving and eventual collapse. In addition to that, the warm firn event and the warm air associated with the atmospheric rivers can also disintegrate the sea ice in front of the ice shelf, removing this protective barrier, which then allows ocean swells to directly impact the front of the ice shelf, which also applies the stress and could also trigger their collapse as well. There have been two notable examples of ice shelf collapses on the Antarctic Peninsula that have been linked to intense atmospheric river activity. One was the collapse of the Larsen A ice shelf in 1995 and the collapse of Larsen B in 2002. And for reference, this image here shows the Larsen B ice shelf collapsing in just a matter of a few months, actually. We can see here in this image from January of 2022, a very warm summer where the successive atmospheric rivers created large amounts of melting on the surface of the ice shelf, created a hydrofracturing cascade, which then led to the dramatic collapse of the ice shelf just a couple months later. Now to fit the atmospheric rivers and extreme weather into the context of tipping points, as Flo was describing before, we are well aware of the bifurcation-induced tipping mechanism of ice shelves, as was discussed before. That is when you have warm ocean waters thinning the ice shelf from underneath and causing the ice shelf to retreat past the grounding line, putting it in a new unstable position, which would then cause an acceleration of the ice shelf, leading to its collapse, and putting us in a new reality where the ice flows faster into the ocean, causing sea levels to rise. Now, extreme weather and atmospheric rivers represent another kind of tipping, which we would refer to as noise-induced tipping. And a noise-induced tipping, you still have this barrier from entering a new state, but you have some sort of perturbation that pushes you over the hill into a new system. In this case, extreme weather could represent a noise-induced tipping where perhaps the system is relatively stable, but some extreme weather is just too much for the system to bear and pushes you into an ice shelf collapse scenario. Now I've created this little schematic to kind of explain how bifurcation and noise-induced tipping can go together. So our little ball here is in the current climate state where we're stable and the ice shelves are still providing the buttressing effect on the ice further around the Antarctic continent. But let's say with further ocean warming and ice shelf thinning, we've now reduced the amplitude of the hill that prevents us from entering the new system, which would be the ice shelf collapse. Then let's say we have an extreme atmospheric river event that acts as a perturbation that pushes us over our smaller hill into a new climate state where the ice shelf has collapsed, and now we're in a new system where the Antarctic continent is losing more ice and sea level rise has increased. Now this is still a relatively young research field. There's still many questions that need to be addressed before we can really understand the influence of extreme weather on tipping points on the Antarctic continent. So this is like one area of research that I'll be working on in the future, where we try to address the question of whether a historically strong event, some like a black swan event that we haven't observed in the previous years, happens at the wrong place at the wrong time, would it be enough to trigger an ice shelf collapse? Basically, in terms of timelines, extreme weather could be the thing that pushes us into a tipping point, maybe several decades before we would actually expect the regular bifurcation-induced tipping to cause an ice shelf collapse. So essentially, this event, going back to the dice analogy, is creating a 7-sided dice, an event we haven't seen yet, and seeing whether that is enough to cause the collapse of an ice shelf. So that now ends my portion of the presentation, and I believe that is now all the presentation. So I think all of us will be happy to take questions now from the audience. Thank you very much.
Thank you, Jonathan. Thank you, Anastasia. And I would like to ask if in the audience there are some questions, actually, perhaps a couple of questions, very quick. Okay, so if there are no questions, I really would like to thank Jonathan and Anastasia for putting this event together. And thank you very much. Thank you to the audience here and online. And good COP for those that are finishing the week here. And see you soon, Jonathan and Anastasia. Thank you very much.
Great, thank you.
Bye-bye.